So last time, we introduced a somewhat awkwardly phrased property of a space. So we say that a space X is semi-locally simply connected if every point has a neighborhood such that the inclusion induces the trivial map. Right, so the trivial map, so it sends everything to the identity. Right, so another way of saying this is that loops in U are null homotopic in X. Right, so they might not be null homotopic in U. If we had that property, then we would say that X is locally simply connected. Right, if every point had every neighborhood of every point had a smaller neighborhood that was simply connected. Right, so that would be if we demanded that the loops were null homotopic inside U. Right, but we don't. We just demand that they're null homotopic inside X. Yes?
Can we have an example of a space that's semi-locally simply connected, but not locally simply connected? To distinguish?
Yes. Yeah, I'm not sure if I can come up with it off the top of my head at the moment, but definitely, okay. Yes. Yes. So you should think of semi-locally simply connected as saying that there's like a lower bound on the size of a hole, right? So if you have a hole inside X, then it has some size, and if you get smaller, then there are no holes, right? So you should think of the counterexample is the Hawaiian earrings, right? And so Hawaiian earrings, right? If you look at the right point, then no matter how small a neighborhood you choose, there are holes that are inside that neighborhood, right? So that's what this is asking, is that there's a lower bound on the size of the holes. Okay, and the point was that with this property, we saw that if you have X path connected, locally path connected, and semi-locally simply connected, then for every subgroup there is a covering space. Let's call it X tilde H. Actually, I want base points, so. Such that the image of the fundamental group with this base point is H. Yes?
So I think if you take the Hawaiian earring and then take the cone of it,
Yes.
that will give you a space where we need the null homotopic in X part of the condition. Because if you take like a point in like the Hawaiian earring, you know, the point where a neighborhood will always contain a loop.
Yes.
It still contains a loop if you thicken it a little bit. But if you're allowed to go all the way out to this point, then you can contract it.
Yes, I think you're right. So I think that'll work as the example you wanted. Take the cone over the Hawaiian earring. So it's a contractible space. All the loops are going to be trivial in X. Okay. Thank you. Okay, perfect. So if you have these properties, then we saw that you can construct a covering space for the identity. And once you have a covering space that induces the trivial subgroup, so a universal cover, then you can show that for any subgroup you have a cover. Okay? So that's what we did last time. questions on last time? Yes.
You've said several times, talked about covering maps and also even coverings. Is there any distinction between if something is evenly covered or if it's just a covering map?
Yes, so the definition of a covering map is that you have a basis of the base of open sets that are evenly covered. So being evenly covered is a property of an open set with respect to this map. And then being a covering map is that you can always find sets, open sets that are evenly covered.
Okay. And would every point in, if P from X tilde to X is a covering map, would every point in X have the same number or possibly cardinality of pre-images in X tilde?
Yes, yes. So that's something we proved last week. Yeah, we called it the lifting homomorphism or lifting map or something like that. And but yes, the answer is yes. So the number of sheets is the same at every point. Right? So that's what distinguishes a covering map from just being a local homeomorphism. Right? So the example you should think of is that if you have a covering space and you restrict it to some open subset, then it'll be a local homeomorphism, but it won't necessarily be a covering map. Right? So think of the circle, and then you cover it with some interval like that. That'll be a local homeomorphism, but it's things are not evenly covered because if you have a point over here, then it has two preimages, and over here they only have one. Okay, more questions on last time or last week? Yes.
I can't remember if it was in the lecture or the textbook, but one of those two pointed out that a covering map didn't need to be surjective, I think, but I was getting a little bit confused about that.
Okay.
Maybe does it need to be surjective? Like this, couldn't like an open neighborhood have pre-image, like no open sets?
No open. Well, okay. So I guess you could allow that. If you're working with path-connected spaces, then it's going to be surjective.
You could have like a path component that
sure,
wasn't.
you might have a path component that isn't covered or something like that, and you still call it sure, because as you say, points over there would satisfy the condition trivially. Yeah.
But is that just not something we consider? Because it seems.
Well, I mean, you can consider covering maps for very general spaces, and you don't need to ask for things to be path connected. It's just if you don't have path connected things, then typically what you would do is just restrict to a path component, right? And so, so yeah, that's what you would do. Of course, you can think if you have something disconnected, like let's say you have two copies of the circle and they're covering the circle. Then you could think, well, I do have something interesting here because I can change the circles. So I have an interesting transformation I can do there that preserves the covering. But unless you're studying something like that, usually you'll just restrict to path components upstairs and downstairs and study the properties one path component at a time. More questions? Okay. So we know that for nice enough spaces, every subgroup has a covering space. So then we can ask, well, how many covering spaces do you have for a given subgroup? And so it depends on how you count. So let's say that two covering spaces or maps, x1 tilde x. Well, let's include a base point. Are equivalent if there's a homeomorphism such that, well, the obvious diagram commutes. right? Or equivalently, P1 is equal to P2 composed with F. Okay, so let's say that two covering spaces are equivalent. If that's true, it's easy to check that this is an equivalence relation. And the theorem, let's say you have two of these, so let's say we're in this situation. And X is path connected and locally path connected. Then these are equivalent. If and only if they induce the same subgroup. Okay, so it's the best you could hope for. For every covering space, for every subgroup, we have a covering space, and if you have two covering spaces that give you the same subgroup, then they're equivalent. Okay, so great. So one direction is easy. Right? If we have equivalent covering spaces, then they induce the same subgroup, right? So because you just look at the induced diagram at fundamental groups, and you get one going this way and one going this way, but the F is a homeomorphism, so it induces an isomorphism on fundamental groups. Right? So one direction is easy. The other direction is more interesting. We assume that they have the same image, and we want to show that there is a homeomorphism. Right? So let's call this H1, and let's call this H2, just to save on chalk. Okay, so remember that for covering maps, we have a complete lifting criterion. Right? So given a map from, say, x1 tilde to x, and a covering map P2, we know that there is a lift of P1 to a map making this commute if and only if the image of the fundamental group under P1 sits inside the image of the fundamental group under P2. Right? But in this case, the images are the same. Right? So what we can say is, since H1 sits inside H2 and P2 is a covering map, and we have path connected and locally path connected, we know that there exists a lift of P1 to a map F. Well, P1 tilde it would be. So we're going to.
Don't we have that?
We don't have that. We're trying to construct an F, right? So yes, this is not a coincidence. Yeah.
Good to know.
Mm-hmm. So we can lift P1 to a map, and making the diagram commute. Right, so we have a map, a candidate. It makes this diagram commute. Right, that's the lifting property. Right, that's what it means to be a lift of P1. So you have this.
Then shouldn't it be x2 tilde?
It should. Thank you. Thank you. So it makes that diagram commute, and we have to prove that it's a homeomorphism. All right. So, okay, well, we also know that H2 sits inside H1. So there's also a lift of P2 to a map, call it G, from x2 tilde x2 to x1 tilde x1, making the appropriate diagram commute. Okay, so in particular, right, let's say you look at x1 tilde, and you apply f and follow with g, then you end up with x1 tilde, and the point x1 tilde goes to the point x1 tilde. And this sits over xx naught. Okay, so this is a lift. Well, this lifts P1 along P1 with this base point going to itself. Right? By uniqueness of lifts, we get the same diagram if we put the identity map here. Right? So because lifts are unique, this has to be equal to the identity. Right? So by uniqueness of lifts, right? And similarly, f composed with g is equal to the identity on x2 tilde. So f is a homeomorphism. So excellent. We have the covering spaces for nice enough spaces are equivalence classes of covering spaces correspond precisely to the subgroups. So let's state that. So if X is path connected, locally path connected, and semi-locally simply connected, then we have if you look at coverings up to equivalence, this corresponds to subgroups. Right, so this is a bijection where you just send P to the image of the fundamental group. So this is if you keep track of base points, right? But as we mentioned last week in the proof of this, it's important in this statement that you have a covering space and a choice of base point that makes this happen, right? If you were to change the base point, you're not guaranteed to get the same group. Because as we saw once upon a time, changing the base point gives you a conjugacy isomorphism between fundamental groups. So if you're looking at subgroups, then this conjugacy can give you different subgroups, right? If you conjugate by some element of the group, you get possibly a different subgroup. Right? So let me state that as part of the theorem, and then I'll give an example to show you how that happens. So let's just say and. If now we just have covering spaces up to equivalence, but without fixing the base point, then this is in one-to-one correspondence with conjugacy classes. Of subgroups. Of pi 1x. Right, and so of course the map would be the same. You give me a covering, and then I look at the induced group, but I look at its conjugacy class. So here's an example. So let's say our space X is just our good friend, the bouquet of two circles. And you were to look at a covering that looks like this. Right, so one of these goes up, one of these goes down. Right, then let's label, if this is x1 tilde, and this is x2 tilde, and this is x naught, then notice that the image of x tilde with x2 tilde. Okay, well, if you're looking at loops based at this point, and then you look at their image down here, then this loop is going to give you B, right? But you don't have anything over here that would give you A. Right? If you were to go like this, you would get A squared, right, down here. Because this one would go down to an A, and this one would go down to an A. So this contains B, but not A. Whereas if you use this base point, then of course this loop comes down to an A, but you don't have anything that would go down to a B. This contains A but not B. Now if I want to go between them, I could pick a path that starts at one of them and goes to the other one. Right? So say we pick, let gamma be so here's x1 tilde. So let's just say you do this, and then you do this to get to x2 tilde. So then x tilde, x1 tilde. This contains, and so at x1 tilde, this contains the image of, say, gamma dot A dot gamma bar, which would be, no, BA, then A, then B inverse, A inverse, which is the image of gamma, then A, then the image of gamma inverse. Oh, did I want to do A or did I want to do B? Gamma bar, yeah. I think I wanted an x2 there. Right, so gamma bar would start at x2 tilde and go down to x1 tilde. So then once you get down to x1 tilde, then you can do an A, and then you go back up to gamma to end up at x2 tilde. Right? So this contains this, and in fact, so if you do this, the image of gamma, then the image of pi1 of x tilde, x1 tilde, and then the image of gamma inverse, you get the x tilde x2 tilde. Right? So you see that up here, changing base point has this effect where you're composing on both sides by a path and its inverse, right? So in this space in x tilde, that's just some a path that doesn't have anything to do with the fundamental group because it starts at one point and ends some other point, right? But once you project that path down, because it started at one preimage of the base point and ended at another preimage of the base point, it projects down to a loop. So now it's an element of the fundamental group downstairs. And so this isomorphism that you have actually projects down to an isomorphism by conjugation inside the fundamental group downstairs. Right? So that's why when you ignore the base point, you end up with conjugacy classes of subgroups. Okay? Questions on this? It's the sort of thing that I think is simpler by an example than by writing it out. But of course, this works in general. Okay, great. So, as we saw, this was just the path lifting property. So the path lifting property also tells you shows that if x tilde is a simply connected covering space of X, which is path connected and locally path connected, then X tilde is a cover of any other covering space of X. Right? So the fact that this is simply connected means that the condition we have for being able to lift a map is automatically true. Always holds. Right? So you can lift and you'll end up with a cover of any other space. This is why it's called the universal cover. Right? So, so we've now justified both the use of the word the and the use of the word universal. Right? So the because it's unique up to equivalence, and universal because it covers any other covering space.
Why is it that the path lifting property is what shows that this covers any other coverings?
Right. So it's just like in the proof over here, right? So we had a condition on the fundamental groups, and we wanted to show that there existed some map between x1 tilde and x2 tilde, and then to prove that it's a homeomorphism, right? So to see that there was such a map, what we used was the lifting property, right? We said, okay, this inclusion is equality, but in particular, an inclusion of fundamental groups gives us a map between the two spaces, right? So the idea is you can do the same thing, but this condition, this inclusion will always be true because H1 will be trivial. Okay? More questions on this? Okay. So instead of looking at equivalence classes of covering spaces, we could have defined a partial order on covering spaces by saying, well, you know, two are comparable if one covers another one, right? And so you have that partial order on covering spaces, and you have a partial order on subgroups by being a subgroup, right? And so it turns out that, in fact, there is an equivalence of partially ordered sets between covers of a space X and subgroups let's fix a base point. And of course, we want X to be path connected and locally path connected. And semi-locally simply connected so we can guarantee existence for each subgroup. So this is known as the Galois correspondence. Because it's analogous to what happens with Galois theory, where you have subgroups of the Galois group and field extensions. Right? In fact, Grothendieck showed that it's more than an analogy, that you can make a single theory that does both, at least if you restrict to finite covers and finite field extensions. Right? Yeah, so there's a nice book entitled Fundamental Groups it's titled Covering Spaces and Galois Theory, something like that. I don't remember the author, but if you email me, I can let you know, which is good.
Is there a connection? We proved the existence of a covering space for any subgroup of the fundamental group with like specific conditions on the space.
Yes.
Does that correspond to like Galois extensions or something like that? Like there's only.
Well, I think Galois extensions corresponds more to normal covers, which we're about to get to soon. But what it is, I mean, not to keep you in suspense, is we're going to say that cover is normal if the induced subgroup is a normal subgroup. Okay. Great. So that's sort of the meta theory of covering spaces, right? So existence and uniqueness and correspondence. So now if you have a covering space, then we're going to look at it more closely and see what you can say about the spaces, right? So first thing is that if you have a covering space, there's an action on the fibers. So let's say you have a cover, and you have an alpha in pi 1 of x, x naught. Then you can define L alpha in the symmetric group of the fiber. Right, so this is a discrete set. So by the symmetric group, we just mean bijections.
What's discrete? Oh, discrete. Okay.
Yeah.
Not finite group.
That's right, yeah. So of course, that's from the covering space property. You have neighborhoods that will have separate images. Okay, so we're going to define this by, and okay, so it's going to be a little backwards in a moment how we define this, because we want the map that goes from elements of the fundamental group to bijections to be a homomorphism. And because we compose paths by concatenation and bijections by function composition, and they go on opposite sides, we're going to define this bijection the opposite of how we've been doing it. So instead of lifting the left endpoint of the path, we're going to set the right endpoint of the path. So by L alpha of a point x tilde is equal to alpha tilde of 0, where alpha tilde is the lift of alpha to a path ending at x tilde. Right. Or if you like, you take the inverse path and then you lift that the usual way and look at the endpoint. Okay, so So as I was saying, if you have two loops, and you look at the symmetry corresponding to the concatenated loop, then you get the composition of the bijections. Right? This is because this, at some point, is equal to the lift of the concatenation evaluated at 0, where this lift is the one that ends there. Right? So, well, if you want to know where this one starts, we're trying to figure out where this one starts, right? But this lift, so we're looking at where this one starts, but this lift ends at b tilde of 0, where b tilde is the lift that ends at x tilde. So this is L alpha of L beta of x tilde. Okay, so that's why we define it as the left endpoint when you fix the right endpoint, so that this would work.
Why can't we just use alpha total of 1? Oh, I guess it.
Right, because you would end up with this equals L beta composed with L alpha, right, which is fine. It's just not what we want. Right. Okay, so let's use that example and see what we're doing. Right, so let's have one loop here, and then like that. One loop there, sitting over. Okay, so let's call this point 1, this point 2, this point 3. This loop is A, and let me reverse the arrow so it matches my notes. Okay, so let's look at LA of 1. Oh, and I should put arrows up here. Okay, so we lift A to the path that ends at 1, right? So A lifts to things on this side, right? And the one that ends at 1 is this loop, right? So it ends at 1 and it begins at 1. So LA of 1 is 1. Right? LA of 2, okay, so here's 2, here's A. I'm going to lift A to the path that ends at 2, right? So if I lift A, I have these three choices. The one that ends at 2 is this one, right? It began at 3, right? So LA of 2 is 3. LA of 3, okay, I'm going to lift A to the path that ends at 3, right? So that's this one. And it began at 2. So this is 2. Right? So here we have a map from pi 1 of the bouquet of 2 circles to the permutations on 3 elements. And what we just saw is that A gets sent to the permutation 2, 3. Right? B, if you work this out, gets sent to 1, 2.
Will it always generate the symmetry group?
No. No, if I had a trivial cover, like, say that, right? So cover the circle by 2 disjoint copies of the circle, then you won't get anything interesting, right? You always get the identity permutation when you lift. Right, so we refer to this as the action of pi1 of x, x naught on the fiber inverse image of x naught. Okay, so now it turns out that for x a nice enough space, so say path connected, locally path connected, and semi-locally simply connected. A covering space can be reconstructed from the action of pi1 on the fiber. So you end up with a further equivalence between actions and covers. If you demand that things be, the cover is also locally path connected, then you do get a transitive action. And by it turns out, what I mean is that you can read a proof in the book, but I'm not going to do it. Okay, so the point, of course, is all of those assumptions are the assumptions we needed to construct the universal cover, right? And we had a very explicit description of the universal cover. It's just the fundamental groupoid with a fixed base point, right? So what the book does is it uses that description and the action of pi1 on the fibers to project down to a covering space that has that action. Okay. But anyway, I'll let you read about it in the privacy of your own home. Okay, wonderful. So now, vector transformations. Also known as covering transformations.
Can I just ask a question about what you said?
Please.
before again? I think I'm having trouble understanding what you mean by reconstructed. So are you saying that we constructed this covering space based on?
So no, what I'm saying is those hypotheses give you a universal covering space, right? And they give you a very explicit description of what that universal covering space is, right? What the statement, the claim is over there is that if you give me an action you want me to have on the fibers, right? So I have some set and I have some action of the fundamental group on that set, then the claim is that there is a cover where that is the action you would have gotten,
Okay.
right? Had you done this lifting, right? And the way the proof goes is, well, take the universal cover with the explicit description you have, and then take a quotient of it, make some identifications, and you will end up with a cover that does the right thing on the fiber.
So we could have come up with this covering space based on the action.
Yes. So the covering space corresponding to an action, you can find inside the universal covering space. Yeah.
It's unique, right?
It is unique up to equivalence.
So
Yeah.
by reconstruction, he means like I'm thinking of a covering space. It has this action, and then you say I know what it is. I'll remember what it is.
Right. Yes.
Out of curiosity, is there a term for path connected, locally path connected,
Semi-locally simply connected. That yes.
I'm just
No,
writing
that
down a bunch of letters, and
Uh-huh.
if X is a pixelisk space, then
there you go. Not that I know of, although it would not be a bad thing. Yeah.
Just do some research on them. Maybe we can
Aha,
call them
we
Alvin
can.
spaces.
There you go. Or we could call them Hatcher spaces, just to thank him for the free book. Yes, so. So what is a deck transformation? This is just the isomorphisms of a covering space. They form a group. Which will denote g of x tilde, or if we want to be precise about all of the objects involved, we might call it deck of the cover. Right? So we defined equivalence classes. So by isomorphism, I mean the homeomorphisms that commute with the projection, right? So the things that give us an equivalence of covering maps, right? So it's easy to check that they form a group under function composition. So why are they called deck transformations? Well, you're supposed to think that like a deck of cards or something is covering a card. And so you're making moves that take one card to another one. But because they have to commute with the projection down to x, you're not allowed to do, move part of a card somewhere and the other part somewhere else, right? The card has to move all together, right? Yes?
Can you say again what you mean by the isomorphisms that are coming?
Yes. So an isomorphism, or I guess you could say an automorphism, because we're going to keep the same cover, is a homeomorphism from x tilde to x tilde such that this diagram commutes, right? So that it preserves the fibers of P.
So does isomorphism mean anything when you're not in the context of covering spaces?
Well, of course, isomorphism means something all over the place, right? So you always have to, if you want to be careful, you should always say an isomorphism of something,
Okay.
right? So this is an isomorphism of covering spaces.
Okay. And is this always going to be an automorphism? Or can you have an isomorphism of two different covering spaces?
Well, so that we call an equivalence
Okay.
of covering maps or spaces. Yeah, so here we're talking about the self-equivalences. And the point is that in order for it to form a group, you have to be able to compose. So that's why you want to fix the one.
So just to give an example, to make sure I'm getting the right intuition.
I'm about to write down examples.
Okay, then go ahead.
Excellent. Yeah, but so what example did you have in mind?
Oh, I was thinking if we take the universal cover of the circle
Exactly right.
and then like shift it up or down a couple levels, basically.
Right. So for R as a covering of the circle, the deck transformations are translations by integers. Right. So the group of deck transformations is the integers. Right? And in fact, that's how we found the fundamental group of the circle originally. If we look at the one we've been playing with today, here the deck transformations is just the identity. Right, so here's the trivial group. So the unique lifting property, as we'll write down in a moment, tells you that a deck transformation is entirely determined. If everybody's connected, deck transformation is determined by what you do to a single point, right? And here, you can see that, well, this point has to be sent to itself, right? As soon as you send a point to itself, you send the whole thing to itself. So this has to be the identity. On the other hand, if we have a graph like this, say, a cover of the same space, but now just like this, like a pumpkin, then of course here you could take one point to the other one, and that would be fine with respect to the projection, right? So the deck transformations here is C mod 2C.
What did you say the conditions for this, like, one point determines the whole thing?
So I'm about to write that down, but it's the unique lifting property for covering spaces. So what you need is path connected and locally path connected.
So for this one with the style, if you fix one point, that would determine the entire map? And
That's
we're
right.
not getting, like, stretching out R more.
Well, the problem if you stretch out, so say over here, if you stretch out R more, then it doesn't commute with this projection, right? So you don't get to change this one, unfortunately, or fortunately, right? So yeah, so then the integers have to go to the integers. Right, so as anticipated by the unique lifting property, if x tilde is path connected. Okay, so all we need is, right, for uniqueness, remember we had a weaker condition than for existence of a lift. So for uniqueness, it's enough that x tilde is path connected. Then a deck transformation is determined by where it sends a single point. So for example, only the identity can fix a point. Okay. So we're going to say that a connected cover is normal or regular or Galois if for any 2 points in the inverse image of a single point, there is a deck transformation. That takes one to the other. Right, so of course there's at most one if x tilde is path connected. So we'll say that it's normal if this happens. So, okay. If we want such a thing to exist, then we have the lifting property. So we know when you can take a, say, the covering map and lift it to a map between x tilde and itself, right? What you need, so if x is reasonable, let's say, then you would have this deck transformation exists if and only if the image of pi1 of x tilde with one base point is equal to the image with respect to the other base point. Yes. But we know that that's equal to the conjugate by the image of any path that joined these base points downstairs. Right? So this leads you to think that if you have a regular cover, then the image of the fundamental group should be a normal subgroup, right? Because conjugation should give us the same thing, right? So that's why it's called a normal cover, because you do indeed get a normal subgroup. So. Right. No. So I do. So you, in this case, you just needed to be able to use the lifting property, right? So let's say path connected and locally path connected. But by that I just meant don't worry about the hypotheses at the moment. Just think about what you're going to need for this to work, right? So this is what you're going to need, right? So here's a formal statement. So we'll put the hypothesis in. So proposition. Let's say that X is path connected. Locally path connected. X tilde is path connected. X tilde, X naught tilde to X, X naught is a covering map. And let's say that H is equal to the image of the fundamental group. Okay, so the first thing we want to show is that you have a normal cover if and only if H is a normal subgroup. Right, for the second thing, we'll first recall that the normalizer of H consists of all of the elements, in this case the fundamental group, such that GHG inverse is equal to H. Right, so the normalizer is the all of the subgroups of the elements of G that do make H look normal, right? And it turns out this is a subgroup of G, and H is normal in N of H, and it is the largest subgroup of G in which H is normal. So recall that. Then part B is that the deck transformations are isomorphic to the quotient of N of H by H. Right, so in particular, if P is a normal cover, then the normalizer is the whole fundamental group. So G is the quotient of the fundamental group by H, G of X tilde. And if X tilde is the universal cover, then G of X tilde is the fundamental group. Of course, isomorphic. Right? which finally brings us around full circle because the deck transformations of this cover give you the integers, and this covering space is simply connected. So this does give you the fundamental group of the integers. The fundamental group of the circle is the integers. Yes. Yeah, not as exciting.
The integers aren't really fast enough.
Yeah. Okay, so proof. So we've basically already done A, but because it's useful for the proof of B, let me just write down the argument. So changing base point. From x naught tilde to x1 tilde corresponds to conjugating H by an element so this is a loop in X that has a lift with a lift that connects X naught tilde, well, let's just say with gamma of I equal xi tilde for 0 and 1. Right, so as we saw earlier today, all you're doing is taking a loop downstairs that lifts to a path between the two base points upstairs, and then you're conjugating by that. So then this element of the fundamental group is going to be in the normalizer precisely when the image of the fundamental group with one base point is equal to the fundamental group with the other base point. And that's the same as saying that there is a deck transformation with tau of x naught tilde equal x1 tilde by the lifting criterion. So A follows.
So this whole thing follows from your representations of universal cover, like you can see it from there.
You could see it from there, but in this case, we don't know that we have a universal cover. But it follows more generally just from the lifting criterion, right? Like everything we've done today, it's all the lifting criterion for covers. Right, so the lifting criterion is about inclusion of fundamental groups, and so that's why when you have equality, you get a deck transformation. Right, so the lift is actually a homeomorphism. Okay. Now for B, so we want to show that the space of deck transformations is a quotient of the normalizer. So what we want to do is take an element of the normalizer and define a deck transformation so that you get a homomorphism whose kernel is H. Right? Okay, so start out with an element of the normalizer. And then define a deck transformation. Be the deck transformation such that. So to determine a deck transformation, I only have to tell you what happens at a point. So let's say that T sub alpha of x naught tilde is equal to alpha tilde of 1 with alpha tilde the lift with alpha tilde of 0 equal to x naught tilde. Right? So I look at this base point and I tell you where to send that one. right? And then you take the unique deck transformation that does that. So let's check that this is a homomorphism. So if you concatenate two loops, let's see what happens to this base point. So of course, by definition, that's just the right endpoint of doing this. Right? So the right endpoint of doing this is going to be the right endpoint of the lift of beta. Right? But here, we're lifting this whole path by saying where it starts. So you can think of that as saying, well, I'm going to lift alpha just like this. But when I lift beta, I don't want it to start at x naught tilde, because if that happened, then I couldn't concatenate. I want it to start at wherever it is that alpha tilde ends. Right? But that's exactly alpha tilde of 1. And I can send x naught tilde to alpha tilde of 1 by this. So I have a translation, if you like, of the covering space that has the property that it sends this point to that point. So this is just going to be this concatenated with what you get by translating the lift of beta tilde and then evaluating at the right endpoint. Right? But of course, the right endpoint, well, I only care about the second path, tau alpha. And that is tau alpha of tau beta of x naught tilde. Right?
Can you say one more time how you got from the first line to the second line, right?
Sure. So this is the lift of the concatenation alpha dot beta, right? So I know that there's a unique lift of alpha dot beta once you tell me what the left endpoint is, right? But now I want to think about that in terms of lifting alpha and lifting beta separately, right? So I know how to lift alpha because I know what the left endpoint is supposed to be, right? But now when I lift beta, I can't use just this lift, which I'm denoting by the tilde, right? If I did beta tilde, then that would start at x naught tilde, right? And if it started at x naught tilde, then I don't know that I can compose this, right? Because who knows where alpha ended, right? However, I can take a homeomorphism that commutes with the cover, this tau alpha, and it'll send this path to some other path, right? And I know that this other path will be a lift of beta, and I know that it'll start at tau alpha of beta naught of 0. Beta naught of 0 is x naught tilde, and tau alpha of x naught tilde is alpha tilde of 1. So then this composition makes sense, right? And because lifts of paths are unique, once you pick an endpoint, this is the lift of that one. Right? So then I get this, right? So I know that at this point, this deck transformation and this deck transformation coincide. But of course, deck transformations are determined by what they do to a point. So they have to coincide everywhere. Okay, so we have a map, this tau, from the normalizer, and it is a homomorphism, and it is surjective, right, by the above. So because I can join, you tell me where you want x naught tilde to go, and I just pick a path that joins them. So we just have to figure out what's in the null space. So notice the null space consists of classes in N of H. So what do we need for this to be in the null space? We need tau alpha to be the identity. Exactly, so we need it to send a point to itself. Exactly, right? So consists of those elements here that lift to loops at x naught tilde, right? But when we first studied the image subgroup, that's exactly what it takes to be in the image, right? I.e., null space is the image of the fundamental group upstairs with base point x naught tilde, which is what we're calling H. So tau induces an isomorphism as required.
I'm puzzled with, like, you remember the action on points the on fibers you defined?
Yes.
And like this weird loop space with two, like the 8
Yes.
above 8. So there was some non-trivial action, right? Like 2 goes to 3, 3 goes to 2.
Yes.
Whereas the deck transformations there were empty, like
Yes.
trivial. But it seems like you're using whenever you have a path that leads, whenever you have a loop that leads to a path, you actually there's a deck transformation that maps that point to the other point.
That's right. So it's an important point that this is not the lifting correspondence that we did before. So I was about to say that, in fact. But yes, good, very good observation. Yeah. So this is not the lifting correspondence. And in fact, that covering space that we did with the 3 base points above the 1 base point for the bouquet of 2 circles is a good example to work that out. But I'll let you all work it out. Yes, it is, in fact, one of the exercises in Hatcher, but I did not assign it on the homework. Nevertheless, a fun exercise to do. Okay. That is a good place to stop. So we'll pick it up there on Thursday.